So let's dig into the fundamental particle of chemistry, which is the atom. And to do that, we're going to look at some philosophical implications of atomic structure and a little bit of the history of how we got to where we are. And if you think back to our last topic, when we were talking about the classification of matter, if you look across the bottom of this kind of bifurcating system, we have elements and compounds as the pure substances and homogeneous and heterogeneous mixtures on the other side. And so what we're going to do over the next several months is we're going to work our way across this diagram, starting first with atomic structures and elements on the periodic table. And then we'll talk a little bit about how elements form compounds. And once we do that, we'll talk about what happens when we dissolve those things in waters to make homogeneous mixtures or solutions. So here's the million-dollar question. What is the smallest particle? Think about this for a second. What do you already know about chemistry? And if you had to tell me what you thought the smallest particle is, what would it be? All right, so keep that in your head. And let's look at this next diagram. So within chemistry, right, we have this kind of structure for compounds. They could be either molecules or formula units, which we'll get to later. But here we have a molecule, which of course can be broken down. That molecule can be broken down into individual atoms, protons, neutrons, and electrons, or protons and neutrons surrounded by electrons. The protons and neutrons break into a smaller piece that we would call the nucleus. Within each of those nucleuses, we have protons and neutrons. And protons and neutrons are made of these particles called quarks. The U and the D stands for up and down. There are two different types of quarks. An electron, if we go all the way back here to the atom, an electron is actually a particle roughly on the same size scale as a quark that's called a lepton. And as far as we know at this particular point in time, those are the two smallest bits that exist. But are they in fact the smallest bits? And how would you know? Well, there are two possibilities for the structure of matter in the universe. Either matter is infinitely divisible and can be broken down into smaller and smaller parts, or there is some fundamental bit that you can no longer break down any further. And the history of the development of atomic theory is an idea that that fundamental particle would in fact exist, and that fundamental particle Greek philosophers refer to as atoms. The word atom comes from the Greek atomos, which means indivisible or uncuttable. Greek atomism is more of a philosophical atomism, and really this question of is matter infinitely divisible or is there a fundamental particle is itself a philosophical question, because there is no way to know. If matter is infinitely divisible, well, you can never do anything an infinite number of times because the history of life on this earth is going to be finite. Likewise, you can have the smallest particle that you know of now, but there's nothing saying there's not going to be some technology down the line that is going to help you break that particle into smaller pieces. So you can't ever resolve this question scientifically. It is a philosophical question, and of course that's where the existence of this began. When we go into the history of Greek philosophy, there are two philosophers, Leucippus and Democritus, who are often credited with the first kind of well-known written account of atomic theory. And this was not an experimental program on their part. They were wrestling with the philosophical question of infinite divisibility versus fundamental particles, and they simply fell on the side of there having to be fundamental particles, and there are philosophical reasons for wanting to take that particular position. Democritus was a student of Leucippus, and most of what we know about Democritus actually comes from the writings of Aristotle, where he grapples with this atomic theory and eventually comes to some other conclusion. But for Democritus, atoms were the basic building blocks of nature, and that they were in constant motion, occupying what was otherwise empty space. The atoms of Democritus were not the atoms of the periodic table that we are accustomed to in modern science, but there were infinite kinds and shapes of atoms, and matter took on the macroscopic properties of different things because of the size and the shape of their particular atoms. And atoms did not, again, come in elemental forms, but there were desk atoms and hammer atoms and book atoms. Every material substance on the planet had the individual particles that made up the larger objects. So when you think about Democritus and atomic theory, he would talk about iron atoms having spikes or hooks that would cause them to link together, that would allow them to form rigid structures that weren't easily changed because their atoms at that small level had some kind of feature that caused them to lock together in strong, rigid forms. Water, on the other hand, would have smooth, round atoms that were very easy to move past one another. The atoms of lemon juice, for example, would have sharp, pointy edges, which is why when you tasted lemon juice, there was a sharp taste to it. It kind of stung the taste buds in your mouth because of the shapes of the atom. And this is how Democritus and his followers would have described this. In Greek philosophy, Democritus was not particularly well followed at the time. And again, there's no scientific program here because there's no science really per se within Greek philosophy. There's a different kind of mode of argumentation. We're actually going to come back to that shortly. Kind of the counter position or the opposing position to Democritus and his infinite number and types of indivisible atoms is Empedocles. Empedocles is around 450 BCE, and Empedocles is the first one that we know that kind of proposed the idea of the four fundamental elements: earth, water, air, and fire, and that matter in the universe is various percentage compositions of these different elements, but the elements themselves are infinitely divisible into smaller and smaller pieces, which allows you to get any possible combination that you can want. Empedocles is fairly important because, as we talked about Aristotle, Aristotle picks up on Empedocles' theoretical framework of fundamental elements, and he attaches to them a set of what he calls qualities. And so not only does he have a classification of matter, but with this structure, Aristotle can generate a theory of how chemical change happens. So take water, for instance, which is wet and cold. If you are to take water and heat it up, what do you get? Well, you get steam after a while, and that steam is just converting the wet and cold qualities of water to wet and hot, which is the quality that you get out of steam. Take earth, which is cold and dry, so think about a dry piece of firewood, and you heat it up, set it on fire, right? You convert that dry firewood to fire, which is no longer cold and dry, but it's hot and dry. And this idea of changing qualities gave an explanation for chemical change, which was embedded in this classification in matter, Aristotle's theory of physics, and his idea of substances and qualities and classification, which also led into his theories of biology. Aristotle had this kind of interconnected theory of everything, and not just within the sciences. Aristotle wrote about political organization, about literary criticism. Aristotle truly had this kind of complete and interconnected theoretical framework that eventually most Greek thinkers adhered to, and into the Middle Ages and the beginning of the scientific revolution, Aristotle was the standard of how to build an interconnected theoretical framework. But you have to understand that Aristotle, again, is not a quote-unquote scientist. And Aristotle would have even said experimentation is a flawed approach. Would have said something to the effect of, you don't torture nature's secrets out of her. Experiments are contrived. If you want to know about the complexity of nature, then go sit in nature and observe it. And that's really how Aristotle built his theoretical framework. And it's not until the time of the scientific revolution that you start to get this approach to science, which is going to try and isolate variables, is going to try and measure and record things in a way that begins to start to pick apart some of Aristotle's theoretical framework. But I want to, again, look at, just from an argumentation standpoint, how Greek philosophers would have argued for or against fundamental particles versus infinite divisibility. And a character who was really pretty good at this in Greek philosophy was a guy by the name of Zeno of Elea. And Zeno went around reading other people's philosophical frameworks and then building paradoxes to kind of tear them down. And one of his famous paradoxes is of Achilles and the tortoise. Now, why would we put Achilles in a race against a tortoise? Well, Achilles is well known for being one of the greatest Greek warriors. He was fast, he was agile. There are all kinds of Greek myths about him having superhuman powers after having been dipped in the mystical river Styx by his mother. Of course, she was holding his hand over his ankle, which is where we get the idea of the Achilles heel, because that didn't get dipped in the river, and so that was his vulnerable point. But Achilles is fast, and we know that a tortoise is not fast. So if Achilles is going to be in a race with a tortoise, the only fair thing to do, give the tortoise a head start. And so here we have the paradox of Achilles and the tortoise. Achilles starts at some position, the tortoise starts at some position ahead of him. The starter to the race stands farther down the line and says, "On your marks, get set, go," and fires his arrow up in the air. It's a slightly less dramatic sequence than firing a blank in the air to start a race, but nonetheless, there we go. And so the tortoise gets a head start and starts off his way. Achilles, being quite fast, is going to catch up to that position that the tortoise started at, but in the time it takes Achilles to get to where the tortoise was, the tortoise will have moved a little bit forward. And so Achilles, again needing to catch up, will cover some of the distance, will cover the distance the tortoise was at his position 2, but in that time the tortoise will have moved a little bit further. And so Achilles again will try to catch up to where the tortoise was, but in the time he catches up to the tortoise will have moved a little bit further. And we can break this into a series of infinite steps again and 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 again. And Achilles never catches the tortoise. But any of you that have younger brothers, sisters, cousins, friends in the neighborhood that you were faster than, you know that you give them a head start only because you know that eventually you will catch them. But in this series of infinite steps, Achilles never catches the tortoise. There's a similar one called the paradox, or the dichotomy paradox, in which you think about covering a distance. So think about standing in the middle of your room, and you want to walk over and touch the wall. Well, in order for you to get to the wall in your room, assuming your room is clean enough to get to the wall, you have to cover half the distance between your center of your room and the wall. And then in order to get the wall from there, you have to cover half the distance again. And then from wherever you are, you have to cover half the distance from that position to the wall, and half the distance, and half the distance, and half the distance. But there is always another division to make. And you should never get to the wall based on this series of infinite steps. It's a paradox, because you know right now if you're in your room, you can stand up and walk across the room and whack your hand on the wall. So this is how Zeno of Elea would have argued that infinity is an absurd concept. A series of infinite steps generates absurdities. Achilles will always pass the tortoise, and you can always walk over and touch your wall. So breaking things into infinite steps makes no sense. Ergo, infinity makes no sense. Ergo, infinite divisibility is improbable at the very least. What we've been talking about in this is the history of Greek atomism, but the Greeks are not the only ones ever to have thought of this idea. Generally, when we teach a history of science course, because we live in America, we teach what's called Western philosophy, and that stems from Greek and Roman philosophy through the Dark Ages into the scientific revolution of Europe. And then, of course, expansion or colonization of the Americas, and eventually scientific breakthroughs in America during the mid-20th century. But there is an entirely other story of the history of the development of science called Eastern philosophy. And atomism has its roots in other places besides Greek philosophy. There is an Indian atomist that predates the Greek philosophers, as a matter of fact. His name is Aruni. The bits and pieces of his philosophy that were extracted. There is this line, particles too small to be seen, massed together into substances and objects of experience. So this idea of particles that clump together into larger particles has this flavor of atomism. And this story is more detailed and nuanced than this, but is not one that I am as well versed on as the Greek philosophy, but just to know that there are other traditions in which atomism is a part of the development of human knowledge. Eventually, everybody comes to this idea that maybe because there are only two possibilities, fundamental particles are infinite divisibility. Once we give up on infinite divisibility because infinity is ridiculous, then we have to really consider this idea of fundamental particles, and then think about how are we going to get at describing, explaining, or observing